My dear friends, today I'll discuss with you some problem regarding the magnetisms. Okay? You know, in electricity or electrostatic, we consider plus Q charge. Now the question is, what is equivalent to plus sign in magnetisms? What is equivalent to Q in magnetisms? The second question is, the Gauss law of electricity. Gauss law in electrostatic. What about the Gauss law in magnetisms? The Coulomb's law of the electrostatic, the force between the charges, was Coulomb's law in magnetisms. And next is, what about the magnetic line of force? Right? There are some basic questions. So let's you come with me in this video. I'll explain to you. तो भाइयों और बहनों, आज का विषय है कि जैसे हम प्लस क्यू कहते हैं तो उसको इक्वलेंट मैग्नेटिज्म में क्या होगा। प्लस का इक्वलेंट मैग्नेटिज्म में, क्यू का इक्वलेंट मैग्नेटिज्म में, माइनस का इक्वलेंट लाइक दैट। कूलम्स लॉ मैग्नेटिज्म में क्या होता है, गॉस लॉ मैग्नेटिज्म का क्या होता है, एक्सेल लाइन, इक्वेटोरियल लाइन के आर्टिकल्स क्या हैं, ये सब हम डिस्कस करेंगे। तो मेरे साथ बने रहिएगा वीडियो में। ओके, और आपको अच्छा लगे तो हमारा चैनल सब्सक्राइब करना मत भूलना। ओके, थैंक यू। सो आवर टुडेस टॉपिक इज magnetic effect of current and magnetisms. Okay. You know very well about electric field. It is a path. Was the electrical line is a path along which unit positive charge moves. Right? Like this is the electrical line, this is the electrical line. It means if you let a free a positive charge, take a positive charge and let it be free in this region, in the region. What happens? This positive charge will then starts moving from left hand to the right hand. Why? Because it is a high positive, it is high negative. So positive charge will experience a force from left to right. So then it will move along this line. So this path, then we call it electrical line, along which unit positive charge moves. Now in case of magnetic field, there is a north pole, there is a south pole. Okay. Now just look. Positive, negative, north, south. Magnetic lines, they are from north to south, like electrical lines from positive to negative. So positive is equivalent to north. So positive is equivalent to the north pole. Negative is equivalent to this south. Okay. So in electricity, the source of positive equivalent to the north pole, source of negative charge equivalent to the south pole. Electrical lines positive to negative, magnetic lines north to south. Very simple. Now, if there is a charge Q here in this field, it will experience a force. How much? Q into E. Q into E. And then this force will be, if the charge is positive, this force will be in the direction of the electric field. If the charge is positive, then F direction, the direction of F will be same as the direction of E. But here in magnetism it is different. Here no problem whether this Q is moving or it is at rest. But here it is a problem. If you put a charge Q here and it is not moving, meaning V equals to 0, then no force will act. So this behavior is different to that from electric field. Okay, if there is a charge, it is at rest in the magnetic field, this charge will not experience any force. So for magnetic force, velocity is must. Okay, velocity should be there. And moreover, it is a cross product. Cross product means the force will depend upon the angle between V and P, because it becomes QVP sine theta. If theta is 0, like theta 0 means if the charge particle is moving with velocity, but it is moving parallel to P, even then there will be no force, because in magnitude the F is QVP sine theta. So if theta is equals to 0, force becomes 0. This is very important. First of all, if the charge is at rest, no force. If charge is moving along the field, even then no force. There is force if there is some angle between the two. Okay. So if the charge is moving parallel to B, no force. If charge is moving anti-parallel to B, theta is 180 here. Here it is B, the V, angle is 180, even then no force. So this force will be maximum if the charge enters in the field at 90 degree. Then maximum force the charge particle will exert. Okay, now from here you find the value of P. If Q is 1 coulomb, 1 meter per second, theta equals to 90 means sine 91. If the particle 1 coulomb with 1 meter per second experience a force of 1 Newton, then this P is said to be 1 Tesla. And remember this definition, then the conversion between Tesla and cos. And remember, Tesla also equals to Weber per meter square. Weber is a unit of magnetic flux. I'll explain to you later on this one. Okay. Now coming here, what is the Coulomb's law in electrostatic? Constant Q1 Q2 by R square. Q1 Q2 two charges separated by R. This electric force is medium dependent. What is medium parameter? Epsilon naught. It is called permittivity of the free space. If you change the medium, this value will change. Okay, epsilon naught will change. This epsilon naught, it will change with the change in the medium. This force is medium dependent. Okay, so if the medium changes, the force will change. And this value, constant value, is 9 into 10 raised to power 9. You already know what is its name. Permittivity of the free space, its value and its unit. Okay, they are very important. Now similarly, now coming in magnetisms, the Coulomb law in magnetisms, instead of Q1, it is M1. It's Q2, it is M2. Now what is M1 and M2? Here they are the poles, magnet poles, North Pole, North Pole and South Pole. There may be North Pole and South Pole, there may be two North Pole, maybe two South Pole, okay? But here, north is equivalent to plus. North is equivalent to plus. But what about charge? Okay, instead of charge, we'll say the strength of the North Pole. It is M1. The strength of this North Pole, this is different North Pole from this one. This strength of this North Pole is M2. Mean if this is a stronger magnet, this North Pole will have more magnetic strength, pole strength. So this pole strength is M1, this pole strength is M2. So the Coulomb law becomes mu naught upon 4 pi. This is constant. Mu naught is called permeability of the free space. It is also medium dependent because mu naught will change with changing the medium. Mean if the two poles, they are in free space, they are in vacuum, they are in water, and any medium, any different medium, then mu will change. But for free space or the vacuum, this value is in SI system 10 raised to power minus 7. Okay, so what is mu naught is called? Write down here, permeability of the free space. What is the unit of mu naught? You do it yourself with the units. Okay, you can, but write it if you know the unit of the pole strength. So this exercise for you. Find out the unit of pole strength. Okay, then Gauss law in electrostatic. So this is electric flux from the closed surface is 1 over epsilon naught times the charge enclosed. So similarly here the magnetic flux, instead of E there is B. But in magnetism this answer is 0 because the single charge in the enclosed, means this is the enclosed surface, it encloses charge Q, and this is the enclosed surface, it encloses a magnet, a pole of strength M, but it is impossible because single pole never exists. Single North Pole, single South Pole, it does not exist in nature. Magnetic pole always exist in pair. They never exist alone. So that's why the Gauss law in magnetism, the right hand side is 0 because the single magnetic pole does not exist. The very, very, very important. Okay, in nature it does not exist. Okay, there's a problem to you. If you find it in the nature, then you will get a Nobel Prize. So try to do research. But yet, it is not found. Now, if the magnetic lines are like this, means they are in the plane of paper, and they are equally spaced, okay, that means the field is uniform. If they are dots like this, that means the field is perpendicular to paper and along upward in direction. Upward means, you know the meaning of upward. Upward means like this, up in along the up direction, okay, towards the reader. So if they are cross means field is again perpendicular, but into the paper means downward in direction. Downward, downward means into away from the reader. So this is perpendicular towards the reader, perpendicular away from reader. So very important. Now magnetic lines. Magnetic lines of force, they are closed continuous curve, north to south pole, outside the magnet, and from south to north inside the magnet. Because magnetic lines always in the loop form, it is different behavior from the charges. Because in case of charge, the electrical line starts from, plus and it ends on minus. But in case of magnetic lines, they always exist in the form of loop. Okay, there is no, beginning and end in case of the magnetic lines. They always exist in the loop form. Now, second point is very, very important. Tangent at every point of the magnetic line of force give the direction of the magnetic field at that point. Mean, if it is shown, this is a magnetic line of force. Okay, this is a magnetic line of force. And do you see, magnetic line of force is the direction of magnetic field? No. This is a magnetic line of force, okay, in a curve form. Then what is the direction of magnetic field? At here. At here, if you are interested, you draw a tangent. Okay, you draw a tangent, and this is a radius of this curve path. Draw a line at 90 degree. So this is the direction of magnetic field. So this is not magnetic field. This is a magnetic line of force. And I am interested here, what is the direction of magnetic field? Then to the radius, I draw a tangent. Okay, and tangent means 90 degree. So this will be direction of the magnetic field. Magnetic field is tangent. Magnetic field at a point is the tangent at that point of the line of force. Okay, it is clear. So don't say magnetic line of force is the magnetic field. No, magnetic field at any point is at the tangent, is the tangent. So second point is clear, I think. So tangent at every point on the magnetic line of force gives the direction of the magnetic field at that point. And no two magnetic lines never intersect. Very, very, very important. And if they are crowded, the magnetic lines, they are thick, mean the field is strong. If they are not crowded, mean thin lines, then field will be weaker. For strong, it is crowded. Okay. So this is all about the magnetic lines. So this simple article, magnetic field due to a bar magnet, okay, on an axial line. So this is a bar magnet. Actually, like this is a north pole, this is a south pole. Again, I am having a question to you. The, pole, magnetic pole is slightly inside the geometrical end. This is a geometrical end of the magnet, but pole is slightly inside. The pole is slightly inside. Why it is slightly inside? You please give your answer in the comments box. Okay, this length is 2L. I am interested here. What will be the field? So if this is north, north is equivalent to plus sign. And Q, instead of Q, this is a magnetic strength M. Again, south is equivalent to minus. And strength is again M. So first of all, find magnetic field because of this north pole. Okay, you will see that the constant and this pole strength M, here it is 1, a pole of strength 1 is here, okay, m into 1 upon distance from here to here. So total distance is total distance from here to here. This is how much? This is r, from center of magnet to this point. From here to here it is L. So this distance becomes r minus L. So r minus L whole square. So this will be the magnetic field. And what about the direction along which the north pole moves? This is north, and you put it here, a north pole of 1 unit strength, so it will move along this side. So this field will be stronger because this pole is nearer as compared to this one. Similarly, you find field here because of this pole. So that will be B2. This is weaker. And B2 means this is a south pole. It will attract the north pole along this direction. So there are two fields, B1 and B2, opposite in direction. Net field becomes B1, B2. So just solving the two, B1 minus B2. So you will get this one. And one thing remember, like in electrostatic, there it is in minus Q plus Q dipole, and 2L, there was a dipole moment, that the Q into 2L, okay, and here we are having the pole strength, mean south pole, north pole, okay, strength M and M. So, and the distance is 2L. So here M into 2L is the magnetic dipole moment, pole strength into the distance. So this is the result. Now you consider the special case R greater than L, then you will get some results. So very simple, no problem. Just solve it, and if you find any difficulty, ask me in the comments box. Now I am coming equatorial line. Very simple. So south pole, north pole. South is equivalent to minus, north is equivalent to plus. Q is equivalent to pole strength, and here unit north pole of 1 unit strength. So for this north, it will repel it along this side. Okay, here north pole, this one is south. It will attract along this side. Divide this into two components, B1 cos theta, B1 sin theta. Resolve B2 into components, B2 cos theta, B2 sin theta. These two components opposite, equal and opposite in directions, cancel out. B1 cos theta, B1 cos theta, they will add up because the same direction. Then find what is cos theta in the triangle and solve it. You will get total magnetic field because of this, magnetic dipole. These two, B1 cos theta and B2 cos theta, they are along the same direction. They will add up. So, this line is equatorial line, and we have found the magnetic field at a point on the equatorial line, and it comes out along this direction, total field. And you solve just the mathematics, you will get the results. Okay, so note down the results. Equatorial line, okay, B1 cos theta and B2 cos theta. Then take the approximation and substitute the magnetic dipole moment. So you will get the results. In case any difficulty, ask me in the comments box. Okay. Thank you very much. तू शाही है प्रवास है काम तेरा, हवा में उड़ना, तूफान अंधेरियों को चीरना। तू शाही है प्रवास है काम तेरा, तेरे सामने आसमां और भी हैं, तेरे सामने आसमां और भी हैं,